For today's class, I want to walk through some alkane nomenclature and another introduction to alkanes. Here are two different groupings of molecules. There are alkanes on the left and things that are classified as not alkanes on the right. And what two elements comprise the alkanes? In other words, what are the only two elements we see here? And the answer is carbons and hydrogens. The things that are not alkanes, you'll notice that the oxygen crops up. So alkanes are composed of carbon and hydrogen exclusively. What is the hybridization of the carbon atoms in alkanes? Well, every carbon over here is bonded to 4 electron groups. If you're not sure where those 4 electron groups are, for example, with this carbon, remember that any bonds that are not shown out of the 4 that carbon is supposed to have are 2 hydrogens. So these all have 4 electron groups, and that means that their hybridization is sp3. What types of bonds are seen in alkanes? It's single bonds. Single bonds are the only type of bonds that we see in alkanes. Things that are not alkenes are things that have double bonds or triple bonds, or atoms that are not carbons and hydrogens. And anytime you see a carbon with a double bond, that carbon is going to be sp2 hybridized, and a carbon with a triple bond will end up being sp3 hybridized. So these are the 3 criteria we look for with alkanes. Alkanes come in a variety of flavors, so methane, ethane, propane, butane, pentane, hexane, and the corresponding number of carbons. The formula for methane is CH4. That's the chemical formula. For ethane, it's C2H6. Propane has 3 carbons. And what we start to see here is a mathematical pattern, that the number of hydrogens is equal to the number of carbons times 2 plus 2. And this is the formula right here, where the number of hydrogens is calculated by the formula 2n plus 2, where n is the number of carbons. So for methane, we stick 1 carbon into that equation, and 2 times 1 plus 2 is 4. For ethane, there are 2 carbons. 2 times 2 plus 2 is 6. For propane, there are 3 carbons, and we put 3 in for n. 2 times 3 plus 2 is 8. For butane, it's 2 times 4 plus 2 is 10. For pentane, it's 2 times 5 is 10, plus 2 more is 12. And for hexane, it's 2 times 6 plus 2 is 14. Notice this pattern. And this rule 2n plus 2 allows us to just know the number of carbons and then immediately predict the number of hydrogens that would be present. So this would be C3H8. This butane would be C4H10. Pentane is C5H12, etc. Alkanes can be either a straight chain, like we see here with butane, and then here's the full Lewis structure of butane, just 2 representations of the same compound, or you can have a branched chain alkane. This is where there is a continuation of carbons in one direction and another continuation of carbons in a different direction. These particular compounds have names, so if it's a straight chain of 4 carbons, we call it butane, or occasionally we use the term N-butane, where N stands for normal, but rarely do we use that designation. And then isobutane is just a common name that chemists started to use for 4 carbons with a branch in it, and it stuck. The chemical formula for butane is C4H10. What is the chemical formula for isobutane? Well, I drew the Lewis structure out here, so now we just have to count. There are 1, 2, 3, 4 carbons, and 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 hydrogens. The chemical formula for isobutane is also C4H10. Compounds with the same chemical formula but different arrangements of bonds are called constitutional isomers. So butane and isobutane are constitutional isomers of each other because we have fundamentally changed the way that the skeleton is built, but we stayed with the same molecular formula. Are there any other constitutional isomers for C4H10? The answer is no. You can pretty much only put 4 carbons in these 2 patterns. No. That seems like a dumb question, but it's relevant to the next one. It's when we get down here to pentane, and we'll talk about that in a second. While we're looking at alkanes, we also have words that we use specifically to talk about a carbon and its hydrogens. If a particular carbon is clustered with 3 bound hydrogens, that's referred to as a methyl group. But if a carbon is bound to 2 hydrogens and 2 not hydrogens, then we refer to it as a methylene group. So this pentane right here has 2 methyl groups and 3 methylene groups. And that's just vocabulary. We're going to look at this vocabulary. Chemists use these words methyl and methylene all the time. What we want to do now is draw all the constitutional isomers of pentane, and we're going to label the methyl, the methylene, and the methine groups. And I haven't introduced methine to you, but when we get to the constitutional isomers of pentane, we'll see some methines. Let's walk through the constitutional isomers of pentane. The first one is the normal or straight chain pentane. So this is the N-pentane. Oh, whoops. Okay, then what we can do is draw pentane. So let's copy and paste this. But what I want to do now is cut off one of these terminal carbons right here and reattach it somewhere else. So I'm going to put it at this position right here. This makes a compound that's called isopentane. If instead of cutting the carbon off the right side and putting it one space over to the left, if I had cut the carbon off of the left side and put it one space over to the left right here, this actually is still isopentane. So this is not a different constitutional isomer. This is just a different view of the exact same molecule, so that was not productive. So now what I'm going to do is cut this carbon off, and I'm also going to move it. And so this now becomes neopentane. And these are the 3 different constitutional isomers of isopentane, right? Or sorry, of pentane. These are the 3 different ways that you can show pentane, the only 3 arrangements that exist. Let's go ahead and look at the number of hydrogens. So if I just hotkey this, I can have it label all the carbons for me. And any carbon that has 3 hydrogens is a methyl group. And so I'm going to go ahead and draw out my structures, and I'm just going to leave the methyl groups black. So if a carbon is black, it's a methyl group, which means I get to leave it alone. Methyl equals black. A methylene is where it's bound to 2 hydrogens. So we're going to go ahead and color our methylene carbons red. There's a methylene carbon right there. We'll make that one red. I don't see any other. Whoops, that did not take. There we go. Yeah, I don't see any other methylene carbons. So my methylenes are red. And that seems silly to not do that in red. There we go. And then finally, methine. And the spelling of methine is M-A-T-H-I-N-E. And let's color that blue. Methynes, methyls are CH3 groups. Methylenes are CH2 groups. And methines are just CH groups. Whoops, missed the H. What do we call CH, or just regular carbons? We don't have a special name for them in this particular nomenclature system. They're not named. The only 3 that we have are methyl for CH3s, methylene for CH2s, and methine for CHs. You can think about these names as actually a way of using a single name to incorporate the carbon and all of its hydrogens. Kind of like a last name is used to identify all members of a family. If you're a single carbon group, you're not actually part of a group. You're just a single carbon, and so we're not going to go ahead and use one of these group names. So these are going to be in blue. And there are only one CH group right there. There's my CH group. And then this carbon right here is not a methyl or a methylene or a methine. So let's go ahead and just color it magenta, just as a reminder that it's none of these. Like magenta is just not anything else. Draw all the constitutional isomers of pentane, it doesn't like the word of, and label the methyl, methylene, and methine group. So we'll go ahead and drop that figure right in there. always get nervous when it thinks. Word and ChemDraw do not always speak the same language. And sometimes that causes Word and ChemDraw to both simultaneously crash. So let's go ahead and save my work. Here I have all the linear alkanes of 5 carbons or less and their names. So here's methane, ethane, propane, and then the 2 different constitutional isomers of butane. I have the regular butane or N-butane and then isobutane, and then the 3 constitutional isomers of pentane. And that N on N-pentane and N-butane is completely optional. And generally I opt not to show it, so I don't care what you do. You need to remember all of these words. We're going to use them, you're going to see them, you should know how to draw them. What is the relationship between the molecules grouped together in boxes? Well, those all have the exact same chemical formula, but a different carbon skeleton, and that is how we define constitutional isomers. So they are constitutional isomers. As the number of carbon increases, the number of constitutional isomers also increase, and so at some point it's problematic for us to just come up with these new common names for each one. So let's talk about the constitutional isomers of C6H14. So we'll go back to ChemDraw, and I think it has to hint because it's hard to keep track of those. There are 5, so let's make sure that we get the correct 5 on there. So these are the ones of pentane. I don't need these anymore. So let's do the easiest one first. So we're going to straight chain this one. Control-Alt-N is the hotkey to give me the name. And then I'm going to do a 5-carbon backbone. So there's my 5-carbon backbone where I'm going to put a branch here. And then I'll also do a 5-carbon backbone where I have a branch in the middle. I can verify that these are different compounds because they should all generate different names. So this is 2-methylpentane, and then this is 3-methylpentane. Other options are the butane versions. So we're going to have 4 carbons in my backbone, and I can either take both of the methyl groups. So if this gives me a total of 6 carbons, or I can take 4 carbons and then I have 2 carbons left to spend, and I can dump them on the same position. You might ask, well, what happens if I dump them on the position on the right instead? Let's show you that. Let's actually clean that up just, okay. And so if I dump them on the position on the right over here, so I'll clip those off. It's clunky. This is way too long to illustrate something that some of you might have already figured out. If I put instead the 2 carbons extra on the position on the right, then it's not any different. It's just the same molecule. It's 2,2-dimethylbutane. This one is also 2,2-dimethylbutane, and this compound is 2,3-dimethylbutane. So these right here are the 5 different constitutional isomers for hexane. And my point in having you draw these out, or having you watch me draw these out, is that they are, it's going to be too many. If we have to come up with common names for every single one of the isomers of every single alkane, we're going to run out of words to think of. And so what you'll notice is that I don't have common names here. I'm starting to use a systematic name. And the systematic name follows specific rules and allows us to evaluate, hopefully, any compound and come up with a name for that particular compound. The nomenclature system is established by a kind of a group of chemists at the International Union of Pure and Applied Chemistry, often called IUPAC. And so it's not the semantics here are a little tricky, but you can't say that something has a common name and a different IUPAC name because the IUPAC allows for common names. So I typically try to say that there are common names and there are systematic names, and both of those fall within the IUPAC. And what we're looking at here is a bunch of systematic names. So let's come up with how we determine the systematic name. The first step is to determine the parent chain. And I'm going to use the grammar helps all I can. So this systematic name is based on us trying to find the longest continuous chunk of carbons. So for this particular compound, the way to find the longest continuous chunk of carbons is pretend like my cursor is a pencil. Drop your pencil on that carbon and try to draw a line across as many carbons as possible without picking your pencil up or without working backwards. And so we can only go 1, 2, 3, 4, 1, 2, 3, 4, 5. So this right here is the parent chain. And it asks me to circle this, which I have a drawing tool. I can do that. So I can draw a circle around my parent chain right there. And then I'm also going to draw a circle around this parent chain right there. Now somebody might ask, well, couldn't you draw a parent chain circle like this? And the answer is yes. Both of them contain 5 carbons. So the black represents one perspective and the pink represents an equally correct perspective. The parent name is based on the number of carbons in the parent chain. You need to remember the names of parent chain lengths of up to 10 carbons. And there's a table right here that gives you the number of carbons and then the parent chain name, and then what we're going to call this as a substituent. So this is a table that you need to know. All right, what is the name for the parent chain in the molecules above? Well, this one has, in the black circle, there are 1, 2, 3, 4, 5 carbons, and in this black circle, there are 1, 2, 3, 4, 5 carbons. Whenever you have 5 carbons, then your parent chain name is pentane. So the answer is pentane. Since the parent name only specifies the parent chain, you also have to describe the branches. These branches are called substituents, and they come off the parent chain. So if this compound over here, this methyl group was not included as part of the parent chain, so it is a substituent, every substituent needs both a name and a locant. And so if I have one carbon that is a substituent, one carbon as a substituent is referred to as a methyl group. Notice that these terms are basically the same. If it's a parent chain, it ends in ANE, and if it's a substituent, it ends in YL. All right, so we've got the parent chain name, that's pentane. We know that the substituent is a methyl group. The last thing we have to come up with is a locant. The locant is the number of the parent chain where the substituent comes off. So for this compound right here, the parent chain is a pentane, the substituent is a methyl group, and I'm asking if this methyl group is coming off of the second position or the fourth position. And at first glance, the correct answer seems like it would be either, but it's not. Always number the parent chain such that the locant is given the smallest number possible. You can always number a parent chain from either end. So if this is my parent chain across the middle, if this is my parent chain right here, then I can either number it 1, 2, 3, 4, 5, or I can number it going the opposite direction, 1, 2, 3, 4, 5. The black numbers would give me 4-methylpentane, and the pink numbers would give me 2-methylpentane. You always want to choose the option where the number of the first locant is the lowest number possible. A branched alkane name is given with the locant number first, and then a hyphen, then the substituent name, followed by the parent chain with no spaces. So this is just an issue of punctuation. So let's go ahead and identify the parent chain here. There are 1, 2, 3, 4, 5, 6 carbons in my longest continuous stretch of carbons, and there is a single methyl substituent that's coming off of, if I start here, it's coming off of the third position, and if I start here, it's not coming off until the fourth position. And so we want to name it such that the position is given the smallest number possible. So this should be a 3, and then so we have a locant first, locant number first, then a hyphen, then the substituent name methyl, followed by the parent chain name with no spaces. So 3-methylhexane. It's a single word. Notice how the numbers and letters are separated by hyphens. Here we are also looking for the parent chain. So 1, 2, 3, 4, 5, 6, 7, 8. So this is some type of octane. If I were to start here at the number 1 position, that would also be an octane. So either one's fine. I either have to start numbering from the left end or the right end. Hopefully you can see that if I number from the left end, then I encounter that ethyl group at the 3 position. If I number at the right end, it would be much higher than the 3 position, so that would be silly. So this is a 3-ethyl octane. And the last one right there is is right here. You may have noticed that the last compound above, which is called 2-methylpropane, also has a common name of isobutane. A variety of compounds have both common names and IUPAC names. And this is just simply the way that IUPAC has worked. And I made the point that I shouldn't refer to this as IUPAC. I should refer to it as a systematic name, because IUPAC accepts both the common and the systematic nomenclature. Sometimes we'll run into a compound that has multiple substituents. Well, it's the same basic rules. We look for the longest continuous stretch of carbons. So that's where we got the term heptane. And then we look, if we number it from the left, then I have a substituent at the 3 position and a substituent at the 5 position. If I number it from the right, then my substituent is at the 3 position and I have another substituent at the 5 position. That's a problem. So the correct answer shows that I numbered it with the 3. Oh yeah, the 3 ends up being the ethyl group. So this was numbered based on the name that I'm looking at right here. It followed the pink numbering system. And the reason for that is if the numbers are the same going in either direction, then the way we break the tie is by comparing alphabetically the 2 lowest numbers. So in the pink, it's actually the 3 refers to an ethyl group, so that's an E. And in the black, if we start from the left and number over, that 3 is a methyl group, so that's an M. E comes before M, so I'm going to choose this system of nomenclature right there. Let's go ahead and look at how we came up with the name for this one. The parent chain name is octane, 1, 2, 3, 4, 5, 6, 7, 8. There's my parent chain. If I start numbering from the left-hand side, then the very first substituent that I encounter is at the number 3. If I start numbering from the right-hand side, then I don't encounter a substituent until the number 4 position. That's an easy win. Always number from the side that makes your first locant have the smallest number. At the 3 position is an ethyl group. At the 4 position is my methyl group. And at the 5 position is my propyl group. Notice, it goes locant, substituent, locant, substituent, locant, substituent. Numbers are separated from letters by hyphens, and there's no spaces in the name. All right, let's walk through a few practice problems. We want to use the following steps to name these compounds. The first step is to identify the parent chain, looking for the longest continuous chunk of carbons, where I have to trace across those carbons without picking up my pen and no backsies. So we'll start here, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. If I had diverted here, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, that would have given me the same parent chain. So you can either go straight or you can drop down. It would be the same compound either way. So we've identified the parent chain as a decane. Then we name the substituents. So this is an ethyl group right there. This is a methyl group, and this is 1, 2, 3, 4. So that's a butyl group right there. And then we're going to number the parent chain to give the first substituent the lowest possible locant number. If I start from the left side, my first substituent occurs at the 3 position. If I start from the right side, my first substituent occurs at the 5 position. We want the first substituent to have the lowest possible number, so I'm going to call this the numbering pattern. The 1, 2, 3, 4, 5, the methyl group shows up at 5, and the butyl group is at 6. Now we alphabetize the substituent names and write out the full name. So that means that I have a 3-ethyl, and I also have a 5-methyl, and I also have a 6-butyl. And then the parent chain name is decane. Now I have to put these 4 pieces together. Decane definitely goes last. But of these ones, the butyl is alphabetized by the letter B, so it's B-E-M. That's how the alphabet works, and so that's how I'm going to put these together. Numbers are separated from letters by hyphens, and then letters just run right into other letters. So this is the correct name for this compound by building it out as an ethyl, a methyl, and a butyl, and a decane, and then putting the pieces together. Notice the parent chain doesn't get alphabetized. It always goes at the end, regardless of the alphabetic priority. Alphabetization only matters for the substituents. I'd encourage you to pause the video and try to come up with a name for this compound. Okay, longest continuous chunk of carbons you should have gotten was 1, 2, 3, 4, 5. So this is a pentane. Coming off of the pentane, I have a methyl group and an ethyl group. I don't have a locant form yet, but I know that E comes before M, so it's going to be ethyl, and then I'm going to have a methyl, and then a pentane. If I number it from the left-hand side, then the methyl group gets the number 2 position. If I number it from the right-hand side, then my first substituent isn't until the number 3 position. Always number it so that your locant gets the lowest number possible. So this is going to be a 2, and the ethyl is coming off of the 3 position. So hopefully that's the name that you came up with. Kind of the last caveat of things that we want to talk about are what happen if the substituents coming off the parent chain end up being the same. So this particular compound has 5 carbons in the parent chain, and there are 3 different methyl groups coming off. The methyl groups are lumped together as a single word methyl, but in front of it we put the prefix for how many of those individual methyl groups there are. So this is called a trimethyl. If there were 4, it would be a tetramethyl, and so on. And then each methyl, even though we've lumped them together, each methyl still needs its own locant. So it's 2, 3, 4 trimethylpentane. Notice how the numbers are separated from each other by commas. That's going to become an issue as we do the practice problems. Numbers and letters are separated by hyphens. Numbers and numbers are separated by commas. Here the longest continuous stretch of carbons is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. If I start from the left-hand side and number, then I encounter a methyl group at the 5 position. If I start at the right-hand side and number, then I encounter a methyl group at the 3 position. Always start at the end. That gets you to a locant as quickly as possible. So that means that this is the end I'm going to number from. So I have methyl groups at the 3 and the 6 position, and I have an ethyl group at the 5 position. Notice that I'm alphabetizing this name based on the E in ethyl, but I do not use the terms di, tri, tetra, etc. for alphabetization. So when I alphabetize this, I'm not comparing an E with a D, I'm comparing the E with the M, and I'm ignoring this prefix that represents a numeric designation. All right, so here are the rules. Identify the parent chain, then name the substituents, number the parent chain, group similar substituents, alphabetize everything, and write out the name. I would encourage you to go ahead and try problem A and B on your own. We'll pause the video, try A and B on your own, and then restart the video, and we'll see how you did. Let's see how it went. On letter A, the longest continuous chunk of carbons is 1, 2, 3, 4, 5, or 1, 2, 3, 4, 5, or 1, 2, 3, 4, 5. Okay, new rule. This particular problem illustrates that often there are multiple identical length parent chains that are not the same. And what you do in that case is, given a choice between multiple parent chains that are all 5 carbons, you choose whichever parent chain has the most total substituents coming off of it. So let's compare pink and black. So here is pink as a potential parent chain that has 1, 2, 3, 4, 5 carbons, and let's compare it to black. And I'm going to use this one right here. It's not the only one I can compare it to, but it illustrates the point. Both the black parent chain and the pink parent chain have a total of 5 carbons. But the black parent chain only has 2 lines coming off of it, so it has 2 substituents. Whereas the pink parent chain has 1, 2, 3, 4, 5, 6 total lines coming off of it. So while there are multiple different parent chains that have 5 carbons, the parent chain with 5 carbons and 6 total substituents is the one that I'm going to choose. So this is a pentane. Coming off of the pentane are 4 methyl groups. So this is a tetramethyl pentane. I also have 2 ethyl groups coming off of it, so it's diethyl tetramethyl pentane. This name right now is garbage because it doesn't identify where on the parent chain anything is, but I have alphabetized it correctly. I'm comparing the E from ethyl with the M from methyl, and I don't worry about alphabetizing the parent chain because it always goes last, even if it starts with 5 letter A's. It's always going to go last. All right, so now let's figure out where the ethyl groups are going to come. It doesn't like the spelling. That's funny. The ethyl groups are going to come off of the 3 position. So even though they have the same number, we still give every locant its own number. So one of these ethyl groups is a 3, and the other ethyl group is also a 3. So 3,3 diethyl. And then the methyl groups are coming off of, and it doesn't matter which end I number it from because it's going to be the same either way. They're coming off of the 2, the 2, the 4, and the 4 position. So that is the correct answer for this compound, letter A. Compound B has 1, 2, 3, 4, 5, 6, 7, 8 carbons. 1, 2, 3, 4, 5, 6, 7, 8. Oh, good. It illustrates the same principle. Let's look at the pink pathway right here versus the black pathway. Both the pink pathway and the black pathway contain a total of 8 carbons. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. Good, yes. The black pathway has, if I just count the lines that are coming off of it, there's 1 line there, 1 line there, and a line there. So it has 3 substituents, whereas the pink pathway has 1, 2, 3, 4 substituents. Given a tie between the number of substituents, the number of carbons in the parent chain, you always choose the parent chain that has the most substituents. So the pink pathway is the correct pathway. Coming off of the pink is 3 methyl groups. So this is going to be a trimethyl. I also have, that looks like a propyl group. And then the parent chain is an octane. Is that right? 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 1, 1, 1. Yep. Trimethyl propyl octane. It happened simply by coincidence to get the alphabetization correct. So the M comes before the P. I was actually intending to do that incorrectly, and then I forgot. And then I would switch it. But now they're in a correct alphabetic order. So this is the correct way to do it. Numbering this, if I start on the left-hand side, then my first locant is at the number 2 position. If I start on the right-hand side, then my first locant is also at the number 2 position. So this problem introduces another level of complexity. The most tedious and correct way to number your parent chain is to make a list of the locants. So if we start on the left side of this compound, then my locants are coming off of the 2, the 4, the 5, 6, and the 7 position. If I start on the right-hand side, then my locants are coming off of the 2, the 3, 4, 5, and the 7 position. Shoot! I thought this would be easier. I need to pick a better example. 2, 3, 4, 5, 6, 7, 2, 3. Yes. Good job, past me. All right. If the locant patterns are different at all. So for example, if this had been a 2, a 4, a 6, and a 7, which it's not, versus a 2, a 4, a 5, and a 7, then you just go down the list until you find the first point of difference. So 2s are the same, 4s are the same, but now the 6 and the 5 wins, so then I would choose the right side. That's what I thought this problem was going to illustrate, but no. When the numbers are the same, going in either direction, then we have to use alphabetic principles to put them in order. So what I'm going to do now going from left is I'm going to put the first letter next to that number. So the 2 is a methyl group. The 4 is also a methyl group. The 5 is a propyl group. And the 7 is a methyl group. Coming from the right-hand side, the 2 is a methyl group. The 4 is a propyl group, and I don't have to do anything more because now I have my point of difference. These 2s are the same, but these 4s are different. Okay? And so once we find that first point of difference, when the numbers are the same, then we just use the alphabet, and the letter M right there is what we're going to use to alphabetize this. So the left-hand side is the way that we're going to number this. 1, 2, whoops. 1, 2, 3, 4, 5, 6, 7, 8. That's the correct numbering. You're like, wow, that's a lot of work. Yes, it is. Okay? All right, so now that we've got the numbering down and we've got our parent chain down and we've got our substituents down, let's start throwing some numbers at this. There are methyl groups at the 2, the 4, and the 7 position. And then there is, that's the trimethyl, and then there is a propyl group at the 5 position. All right, check your answer. Make sure it matches my answer. Also check your punctuation. Make sure that you have commas where I have commas and you have hyphens where I have hyphens. Everything that I've said as far as nomenclature, even this additional complexity of these last 2 problems, is embedded kind of in this particular list. So these are the steps for naming linear alkanes. And yes, again, this is something that you kind of need to memorize. And by kind of, I mean definitely, absolutely have to memorize these steps. And hopefully you're able to apply them enough that memorizing them kind of becomes secondhand. So let's go ahead and use these summary rules to name compound A and compound B. Once again, pause the video, try this on your own, and then restart the video, and I'll walk you through the correct answer. All right, so for compound A, let's go ahead and start trying to pick a parent chain. There is this parent chain, 1, 2, 3, 4, 5, 6, 7, 8, 9. Or there is a parent chain that will show in green. 1, 2, 3, 4, 5, 6, 7, 8, 9. So that when I have 2 competing parent chains, I have to choose the parent chain that has the most substituents coming off of it. The pink parent chain has 1 thing hanging off of it, and the green parent chain has 2 things hanging off of it. So that means that this compound is a nonane, and it is the green nonane. The green nonane has a methyl group coming off of it, and it also has an ethyl group hanging off of it. I need to alphabetize those 2 substituents, so I should have written it in the order of ethyl-methyl. And the numbers for the substituents on the green, if I start at the top, come to the methyl group at the number 2 position and the ethyl group at the number 3 position, those are definitely going to be lower than the numbers I get if I started over here. So that means that it's a 3-ethyl, 2-methyl nonane. That was the easy one. Let's take a look at the harder one. So obvious parent chain, I'm going to try this one. 1, 2, 3, 4, 5, 6, 7, 8, 9. Yeah, 9, 1, 2, 3, 4, 5, 6, 7, 8, 9. So that would be an alternate route. But you'll notice if I start over here, then I'm only going to get, right now I currently have 1, 2, 3, 4, 5, 6 total substituents coming off the green line. If I were to draw a pink line in here, it would have only 1, 2, 3, 4 substituents. 1, 2, 3, 4, yep. So 1, 2, 3, 4, 5, 6, 7, 8, 9. That would give me only 3 substituents. So the green line represents the longest continuous stretch of carbons with the most substituents. I don't see any other options that would give me 6 substituents. So this is a nonane again. Coming off the nonane, I see 3 methyl groups. So that's a trimethyl. There's methyl groups at both these positions. There's 2 methyl groups here and then 1 more right there. And then I also have ethyl groups there. So that's diethyl, and then I have a propyl group. So those are the 3 groups, and I just kind of threw them up there, and now I have to alphabetize. It's M versus E versus P. So alphabetically, the E to EMP is the correct alphabetic order. Numbering this, if I start from the right-hand side, then my numbers of locants from the right occur at the 2 position, 3, 4 position, 5, 6 position, 1, 2, 3, 4, 5. Yeah, so sorry, starting from the right-hand side over here, I end up with something at the 2, and then something at the 4, and then something at the 6. And I could keep going, but it doesn't matter, because if I start from the left-hand side, then I encounter 2 substituents right away. Something at the 2, something else at the 2, and then something at the 3. And all you're looking for is the very first time that they're different. And so this 2 beats that 4, so I'm going to number this from the left-hand side. I'll go ahead and drop those numbers in. This would be 1, 2, 3, that's a 4. I'm getting tired of using my mouse. 6, 7, 8, 9. All right, now let's throw some numbers on here. The ethyl groups look like they're showing up at, that is a number 3. That doesn't look like it, but it is. So that's at the 3 position, at the 6 position are my 2 ethyl groups. So I have 3, 6 dash. alpha capitalization doesn't matter, but it bugs me. So you do whatever you want. So 3 and 6, I have my ethyls. At 2 and 2 and 8, I have my methyls. Dash 2, comma 2, comma 8, I've got my methyl groups. And then at the 4 position, I have my propyl groups. And boom, there's my correct name right there. So let's go back and just kind of review the rules again. So I determined the parent chain by looking for the longest string of carbons. In this compound right here, I found a lot of strings that were 9. If you find 2 or more parent chains of identical length, choose the parent chain with the most substituents. And then you name those substituents, which I did when I just kind of threw this name up here without any numbers on it. Then I number the parent chain. So you want to number it such that the first substituent is given the smallest number. If the first substituent is the same on either end, choose the locant that comes first alphabetically. If it doesn't help, move on to the next substituent. So that's kind of this left-right thing that we've done, and we've added letters in, and we've seen some examples of dealing with that complexity. Finally, we write the name by grouping the similar substituents with the number with the prefixes ditri and tetra, which we did by calling this a diethyl and a trimethyl. We alphabetize the substituents, but don't use those terms, ditri and tetra. That's why I alphabetized it according to E, M, and P. Then finally, use hyphens to separate the numbers from the letters and commas to separate the numbers from the numbers. That's as far as I'm going to go in this particular exercise. These other ones are going to be more useful to you after we talk about lecture 2C. So I wouldn't attempt to try 15, 16, 17 yet. We'll just wait a minute and we'll get to those.